Hey everyone, welcome back to Aero Basics. In this video, we're going to explore how airplanes are classified based on their configuration. We'll talk about how wings, tails, engines, and fuselages are arranged, and why it matters. Then, we'll dive into the key factors that affect how aircraft are designed. And finally, we'll take a quick trip through aviation history to see how it all began. Let's begin with the classification of airplanes. Aircraft aren't just designed randomly, every shape and feature is chosen for a reason. And the overall arrangement of these features is called the airplane's configuration. We'll look at four main aspects: the wing configuration, the fuselage design, the horizontal stabilizer setup, and the number and location of engines. First up, wings. Wings come in different styles depending on the role of the aircraft. High-wing aircraft have wings mounted on top of the fuselage. These offer good stability and great downward visibility, perfect for transport and observation planes. Mid-wing aircraft have wings in the center of the fuselage. They offer good maneuverability and are often seen in fighter aircraft. Low-wing aircraft, with wings mounted underneath, are very common in commercial planes, offering efficient ground clearance and better aerodynamic performance. There's also the sweep angle, straight wings for slower speeds and more lift, swept wings for faster speeds and less drag. Next is the fuselage, the central body of the aircraft. The most common is the conventional cylindrical fuselage, like you see in airliners. It carries passengers, cargo, and houses the cockpit. Then there's the blended wing body, which looks futuristic and smooth, with the wings and body merged together. It reduces drag and increases lift, used in some advanced military and experimental aircraft. Some aircraft also use a flying wing design, where the entire body acts like a wing, with no traditional fuselage at all. Now let's talk about the horizontal stabilizer, which helps keep the airplane balanced in pitch. The conventional tail places the horizontal stabilizer at the rear of the fuselage. It's simple, efficient, and widely used. The T-tail puts the stabilizer on top of the vertical fin, giving better airflow and control, especially in rear-engine planes. Then there's the canard configuration, where the horizontal stabilizer is placed in front of the main wing. This is less common but offers some aerodynamic advantages and control benefits. Engines, the muscle of the airplane. Planes can have one, two, or even four engines. The number depends on the size of the aircraft, the desired power, and safety requirements. Engines can be mounted under the wings, like in most airliners. This improves efficiency and simplifies maintenance. They can also be mounted at the rear, especially in business jets. In some cases, engines are embedded in the fuselage or even placed on top of the wing to reduce noise or protect them from debris. So, what drives the decisions behind all these configurations? It's a mix of science, engineering, cost, and even politics. Let's break down the main factors that influence airplane design. First, aerodynamics. Every aircraft is shaped to fight drag, generate lift, and maintain stable airflow. Designers aim to reduce drag, especially parasitic drag and interference drag that occurs where surfaces meet. At the same time, the wings and tail must create enough lift to support the aircraft. Aerodynamic efficiency is key for performance, fuel savings, and range. Weight matters a lot. The heavier the aircraft, the more fuel it burns. Designers constantly look for ways to reduce structural weight without compromising strength. They use materials like aluminum alloys, titanium, and composites, along with clever structural layouts. Each aircraft has its own mission-specific needs. A fighter jet needs agility. A cargo plane needs volume and a big loading door. A stealth aircraft needs low radar visibility, so it may have wide shapes and internal weapon bays. These layout peculiarities heavily influence configuration. Even the coolest design is pointless if it can't be built efficiently. The configuration must consider ease of manufacturing, assembly line compatibility, and supply chain logistics. Standardized parts and modular designs help reduce time and cost. Cost is king. There are direct operating costs, like fuel, crew, and maintenance, and indirect operating costs, like training, airport fees, and spares. If a design saves fuel but costs a fortune to maintain, it might not be worth it. Airlines and military operators always evaluate performance versus cost. And finally, no single factor decides everything. Design is a balancing act. You might want a lightweight structure, but you still need strength. You want low drag, but you must fit passengers comfortably. Every configuration is a result of compromise between multiple, often conflicting, goals. Let's take a quick detour into history. Modern airplane configurations didn't appear overnight. They evolved over more than a century of trial, error, and innovation. In 1903, the Wright brothers flew the world's first powered airplane, with a biplane structure, canard configuration, and twin propellers. During World War I, biplanes dominated, slow but highly maneuverable. By World War II, monoplanes took over. Stronger engines and metal construction allowed for faster, heavier, and more advanced designs. Post-war, jet engines revolutionized aircraft design. Configurations shifted to low-wing jets with pressurized fuselages and swept wings. In the 1960s and 70s, we saw the rise of jumbo jets, supersonic transport like the Concorde, and experimental designs like the SR-71 Blackbird. Today's airplanes benefit from decades of evolution. Every angle, every bolt, every engine placement, it all carries the legacy of past designs. And future configurations, they'll be shaped by new tech, electric propulsion, blended wing bodies, even flying taxis. So whether it's a small drone or a giant airliner, each aircraft is a carefully tuned machine, built with purpose, precision, and a ton of trade-offs. Understanding configuration is like learning the aircraft's DNA. Thanks for watching this deep dive into airplane configurations and design choices. If you found this helpful, give it a thumbs up and hit that subscribe button. We've got more Aero Basics videos coming your way, and it's only getting more exciting from here. Drop your questions or topics in the comments. I'd love to cover them in future videos. Until then, stay curious, stay inspired, and keep looking up.